Good morning. I will wait one more minute for people to join in. Good morning. All right, I'm going to go ahead and get started. So, good morning, everyone. Today we are going to be talking about something called wave beating. Okay, so wave beating is when two waves of nearly equal frequency frequencies superpose. So just to remind you, that needs to focus a little bit. Just to remind you, when two waves are superposing, that means two waves are combining to make the total wave, okay? And so really this lesson has very, very simple math, but there's a lot that I would like to demonstrate to you guys, okay? So what I'm going to demonstrate to you guys first, maybe you've observed this phenomenon before where you're in a turn lane in a car. So maybe you're in a right turn lane or a left turn lane, and there's a car in front of you, and both your car and the car in front of you have the blinkers on. The turn signal is on. And what you'll notice when that happens is that the two turn signals, okay, the two turn signals are sort of in sync for a while. And then after a while, they go out of sync. And then after a while, they go back in sync. And then they go out of sync. So I'm going to show you a YouTube video that demonstrates this. So what we have is two cars that are side by side, and both cars have their emergency flashers on, and we can see them go in sync and out of sync. So let's observe. So right now they're out of sync. Out of sync. In 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 sync. Okay. So we were able to say that they were in sync because they're almost blinking at the same rate, but not quite. Okay. Another similar phenomenon is, when if you're running around the track with a buddy, okay, and if you guys have run at almost the same speed, what you'll find is that you two are running next to each other. Okay. You two have been running next to each other, and then you will pull ahead of the other person. If you're going a little bit faster, you're running together, but you will gradually pull ahead, and eventually you'll be on the opposite side of the track as the other person. But you're still running faster than them, so eventually you'll lap them, and for a while you guys are running together again. And then you get ahead, you pull ahead, and you're on the opposite sides of the track. Okay? These are all examples that are similar to wave beating. So what does it mean when the blinkers are in sync? Well, that's like constructive interference, because constructive interference is when both waves are up or both waves are down together. Okay, when the blinkers are out of sync, that's like destructive interference, where one wave is high and the other wave is low. Okay, so let's go ahead and take a look at Desmos, where I've prepared some graphs. Okay, so I have a. Oops, I gotta zoom in some. Okay, so I have a displacement versus time graph. Okay. And so here's the first wave. This wave, let's figure out what its period is. All right. Its period is the time it takes to go up and do a complete full swing up and then a full swing down and then come back to center. Okay. So a full period is an up and a down. So right here is a full period, and I can see that that is halfway between 0 and 10 seconds. So the period of wave 1 is 5 seconds. Okay, so let me go back to the document camera really quick. So this is gonna be our example for today. So the period of wave 1 was 5 seconds. All right, which means that the frequency of wave 1, frequency is always 1 over the period. So that's going to be 1/5 of a hertz. Okay, so now let's go to wave 2. wave 2 has almost the same frequency. It has almost the same period as well. So we can see that this wave goes up. So the green wave goes up and comes back down and goes back up again right here. So what you'll notice is that it's right on this crossing right here, which is 6 seconds. So so that means that the period of wave 2 is 6 seconds. All right. So that means that the frequency of wave 2 is 1 over the period of wave 2, which is going to be 1/6 of a hertz. All right. So now let's go back. So now I'm going to show you both waves together. All right, so we have the green wave and the blue wave. And what we can see is that the two waves start out in sync. See how they both have peaks at the same time? They both have peaks at the same time. But because they have different periods, different frequencies as well, they gradually go out of sync until we get to about until we get to about 15 seconds or so, when the green wave is high and the blue wave is low, and then the blue wave is high and the green wave is low. So now they're out of sync. So we start out with constructive interference, and then we get to destructive interference right here. And then at a later time, we go back into constructive interference. So it looks like that happens at about 30 seconds. See how they line up again at 30 seconds. Okay. So going back to the document camera. So basically there's a concept called the beat period, which is equal to the time between consecutive constructive interferences. All right. And so what we can see is that they, at 0 seconds, they're in sync. There's constructive interference. And then again at 30 seconds, they're back in sync. So there's 30 seconds between constructive interferences. Okay? So that means that the beat period is equal to 30 seconds. All right? And then that means that the beat frequency, and frequency is always defined as 1 over the period. Okay, so I'm going to box that in, is going to be equal to 1/30th of a hertz. Okay? Now what I want to notice here, notice that if I do frequency 1 minus frequency 2, that would be 1/5 minus 1/6. Okay, and if I simplify this, if I combine it, this is equal to 6 over 30 minus 5 over 30, which is 1/30th of a hertz, which is the same as the beat frequency. Okay, so in this example, the difference between the two frequencies of each wave is equal to the beat frequency. And actually, this is true in general. I'm not going to prove it, but it is true in general that the beat frequency is equal to the difference between the two frequencies. Now, because a frequency can't be negative, and we don't know which frequency is higher, we put an absolute value here, okay? Just so that the difference is positive. So this is our main equation for today, which is that the beat frequency is the difference between the two frequencies, okay? So now we're going to answer some questions here. So what happens, so I'm just going to do some questions here. What happens as the periods, okay, and or, oh, I should say and. So if the periods are the same, the frequencies are going to be the same. If the periods get closer, the frequencies get closer. The periods slash frequencies get closer together. All right, let's observe on Desmos. So I'm going to make the frequency of the second wave closer to that of the first wave, all right? And what we can see is at 30 seconds, remember, they used to be in sync at 30 seconds, but now they're out of sync at 30 seconds. So I have to actually I have to move the graph to find the next time in which they're in sync. And I can see that they actually go in sync now at 55 seconds. Okay? So the general conclusion is it takes more time for the waves to get in and out of sync as the frequencies get closer. So let's try to understand why that's true. Imagine that you and your buddy are running around the track. So going back to the running around the track example, if you and your buddy are really close to the same speed, then you're going to be running together for a long time. But then once you pull ahead of them, you're going to be on the opposite sides of the track for a long time as well. Okay? So the closer those two speeds are, the more time you spend together, and also the more time you spend apart. So it takes more total amount of time to lap the other person, if you will. Okay? So that is what happens as the frequencies get closer together. Okay? It takes more time to go in sync and more time to come out of sync. All right, next question. What does the superposed wave look like? Okay, because remember, we don't see the individual waves, all right? We see the total wave. So right here, notice that I have f of x plus g of x. So I'm adding the two waves together to get the total wave. So let's see what that looks like. Make these two disappear. And it looks like this. All right. So what you can see is that when the two waves are in sync, we have the amplitude is large. And as the waves go out of sync, the amplitude gets smaller. And then they start to go back in sync again, so the amplitude gets larger, and then it gets smaller. So the amplitude fluctuates. Okay? So that's what it looks like. Oops. Okay, so the displacement versus time graph looks something like this, and it's kind of hard to draw. I'm going to use a guide here. So it kind of looks like this. All right. So these dashed lines are called the envelope of the graph. All right. So you should know what the superposed wave looks like. Okay. Next question is, what if the waves aren't the same size? Okay. What if the two waves do not have the same size? So let's go back to Desmos to demonstrate what happens. So I can see that right here, this wave has an amplitude of 1 because it goes up to 1 and down to -1. And the other wave also has an amplitude of 1 because it also goes between 1 and -1. But what if I make them have different sizes? What if I make this wave have an amplitude of, let's say, 4, and let's have the other wave keep an amplitude of 1. Okay, so these waves have different sizes now. I'm going to have to zoom out for this. All right. So now let's look at what the superposed wave looks like in this case. So you can see that we have constructive interference, okay, and then we have destructive interference, and then constructive, and then destructive. But because the waves have different sizes, they can't completely destructively interfere. Okay? They cannot completely destructively interfere with each other because a wave with a size of 1 can't completely cancel out a wave with an amplitude of 4. All right? Another thing I want you guys to notice, is that the maximum amplitude is 5. See how it goes up to a peak amplitude of 5? And that happens to be 4 plus 1. All right? So when they're constructively interfering, we add the two amplitudes. All right? And then the smallest amplitude we have is right here, which is right at about 3, okay, which happens to be 4 minus 1. Okay? So basically, if the two waves aren't the same size, you cannot have completely destructive interference. And the other thing I want you to know is that the maximum amplitude is going to be the sum of the amplitudes of the individual waves. And the minimum amplitude is going to be the difference of the amplitudes of the two waves. Actually, the absolute value of the difference, because we don't know which one is bigger, and amplitude is always positive. Okay. So that is nice. Next question. How do we perceive the beating of sound waves? Okay, so how would we perceive that? Well, the key idea to understand how we perceive it is that the amplitude of a sound wave is equal to its volume. Okay, so if we go back to Desmos, we can see that the amplitude of the wave goes up and it goes down, and it goes up and it goes down, and it goes up and it goes down. And so, what that means is that the volume, it's going to get quieter, then louder, then quieter, then louder, then quieter, then louder. So what we are going to perceive is we are going to perceive the volume is going to fluctuate or to pulse regularly. Okay, so I'm going to demonstrate that to you. Give me a second. Okay, let me check if there's questions in the chat. All right, so here we go. So what I have is a tone generator. I just found a website that produces a tone, so I can turn the tone on and off. Like that. And then I have a second tab open with the exact same thing, okay? All right, so I have two copies of the same tab, of the same website. So now what I'm going to do is I'm going to shift this one so that this one is at 440 hertz, and this one, or this one's at 440, and this one is at 444, okay? And then I'm going to play them both simultaneously, and let's see what we hear. Okay, so we are hearing the pulsing of the volume, and this is the beat. This is what beating is of sound waves. Now, one of the things I want you to notice is that if we count the pulses, 1, 2, 3, 4, 2, 2, 3, 4, 3, 2, 3, 4, 4, 2, 3, 4, 5, 2, 3, 4, 6, 2, 3, 4, okay? I want you to notice that there were 4 pulses per second. Okay, so 4 times per second. That's a frequency of 4 hertz. Now, what would happen if we took the difference between those two frequencies? It would be 444 minus 440, which is equal to 4 hertz. Okay, so we were able to hear 4 pulses per second. All right. Okay, and that corresponded with the formula that we learned. So that was the point there. If I do that. Now, what happens if the two frequencies get closer together? So I play 440, and then what if I play 442? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that is when I made the difference between the two frequencies equal to 2 hertz, we heard 2 pulses per second. Okay, now what if I make the difference between the two frequencies 1 hertz? We're going to hear 1 pulse per second. 1, 2, 3, 4, 5, 6, 7. All right? So when the difference is 1 hertz, we hear 1 pulse per second. And then lastly, we could say, well, what if the difference between the two frequencies is 0 hertz? All right? So now I make this one. Okay? We just get a consistent sound with no pulsing. Notice how as I start and stop the second sound, I get a different volume each time. So why is that? Why do I get a different volume each time I start and stop sound? Okay, it's because when I start and stop them, I don't know whether I start them in sync or I start them out of sync. So imagine you and your friend are running, and you're running at the exact same speed around the track. That means that if you are on opposite sides of the track, you're always going to be on opposite sides of the track because you're running at the exact same speed. Okay? If you're running together, you're always going to be running together because you have the exact same speed. So what's happening there, the reason that the volume is changing each time I start and stop the sound is because I'm starting the sound, and I might have started them both in sync so that they stay together and they have constructive interference, or I might have started them so that when they're out of sync, so that they have destructive interference, and so it's quieter. Okay? So if you have two sounds of the same frequency and you add them together, the total result could be constructive interference or it could be destructive interference, depending on the starting point of the two sounds. Okay, so I hope that makes sense. One of the uses of beat frequencies is you can tune an instrument by listening to the pulses. Okay, So I'm going to have a bird box moment, and I'm going to make myself blind, and I'm going to tune one frequency to the other frequency, okay? So I'm going to put one of these tones at here. Oh, that's annoying. Okay, so I'm going to put one of the frequencies here, and I'm going to start the other frequency lower. Okay, and I can change this one. Okay, so I'm going to change them until they're the exact same frequency without looking. Okay, so here we go. So I hear no pulsing right now, so those must be the same frequencies. Let's check. 626 and 626. Oh yeah. So you can use the pulsing sound of waves beating to match two frequencies. It's kind of interesting. So that's what I just did. All right. So at any rate, that is my lesson for today. Okay. And I see an interesting comment in the chat, which is it sounds like an airplane almost. And I will explain why it sounds like an airplane when we get to the Zoom room, okay? So that is my lesson for today, and I will see you in the Zoom room.